Hello everybody, welcome to my channel Deep Intelligence Lab. I am finally excited to start this series on exploring AI and machine learning concepts step by step, visually, intuitively and mathematically. If you're a person who is new to AI or wants to delve deeper into the mathematics, then this channel is for you. Once again, welcome to the channel. In this video, we'll be discussing the concept of linear regression. It might sound very simple to begin with, but it has a lot of mathematics to it. So let us start by talking about the deterministic part of linear regression. There is also an upcoming video on the probabilistic part of linear regression. So stay tuned and welcome once again. Now, let us dive deeper into the deterministic story behind linear regression. Linear regression is a machine learning technique that is used to build a relationship between inputs, which can also be called as features and can be represented as x1, x2, and so on, with output or a target variable which can be represented as y. Now, let us look at how this can be represented on a graph. For this representation purpose, we assume we just have a single feature which needs to be related with an output variable or target variable y. Assuming I have the following points on the graph, using linear regression, I try to create a line or draw a line such that we have minimal error between the line and the points. We will discuss further about this error, but for now, we have a line which is basically the linear representation of the relation between the feature and target variable. How do we represent a line? The most common and well-known format is the slope-intercept format, where we represent the prediction of the variable y as y cap equal to mx plus c. Now, if you remember, we have assumed that we have a single feature. But what if we do have multiple features? In such cases, we can represent this as y cap is equal to m1 x1 plus m2 x2, so on mn xn plus m naught. M naught here is the intercept. We can also simplify this into a summation as y cap equals m naught plus summation I equal to 1 to n mi xi. This can be further simplified into a matrix format representation, which can be y cap equals x beta or y cap equals xm. Here, m and beta are basically the weights given to each of the input features. Now, what is our goal? Our goal is to minimize the error, just like I mentioned earlier. How is this error represented? Now, let us go back to the graph and visualize it. The error is the linear distance between the line that we have predicted and the true points x, y. This can also be called as the residual. We represent the residual or error as y minus y cap, where y is the original target variable and y cap, which is the prediction made by the linear model. Now, in general, whenever we want to minimize an error, we often represent it in the format of least squares. But why do we do that? There are multiple reasons, so let's just list them out. First of all, when we represent any error in the format of least squares, we ensure that it is non-negative, because obviously a square cannot be a negative number. It also penalizes huge errors because we end up squaring each of the error terms. Next, least squares is also a convex function which makes our life easier, and we can end up approaching a unique minima. Now, we define something known as a loss function using the least squares approach. We can call the loss function as an intelligent representation of the error. Again, back to the mathematics, we have j of m, which is equal to square of the norm of y minus y cap divided by n. Again, like discussed earlier, we have y cap equal to xm in the matrix format. This can also be expanded as 1 by n into y minus xm whole transpose into y minus xm. Here we are using the basic matrix property where we have the square of the norm of any vector to be the vector's transpose times the vector. So we now have j of m equals 1 by n times y transpose y minus y transpose xm minus m transpose x transpose y plus m transpose x transpose xm. While finding the second term, we use the simple transpose formula where xm whole transpose is equal to m transpose x transpose. We can combine the middle two terms using the scalar property, which states that the transpose of a scalar value will give the scalar value itself. Now, getting back to our original goal, which was to minimize the loss function, which is a representation of the error. To do that, we find the gradient and equate it to 0. Again, the old math technique. So the gradient of j of m can be represented as minus 2 by n times x transpose y minus x transpose xm, which has to be equated to 0, which gives us the following relation. Now, our goal is to find the value of m such that we are able to minimize j of m. So, we send the term x transpose x to the RHS. This can be done using the inverse of x transpose x. So we finally have the relation m equals x transpose x inverse times x transpose y. But this is only possible if x transpose x is invertible. It is a well-known fact that matrix inversion is a computationally intensive task. So performing matrix inversion when we have huge matrices is not an option. We will talk about an alternative approach to this at the end of this video. Now let us try to discuss the simplified version of this matrix format, which is the regular line equation, and we will be solving this only for a single feature. We express the line equation format for a single data point I, which is represented as yi cap equals m0 plus mxi. The loss function would be the mean of all the squares of differences of yi and yi cap. Again, we replace the value of yi cap to be m0 plus mxi. Once again, because we want to minimize the value of j of m0, m, we end up taking the gradients of j of m0, m with respect to m0 and m and equating them to 0. First, we find the gradient of j of m0, m with respect to m0. As we can see, this can be simplified to summation of yi minus m into summation of xi by n is equal to m0. Again here, summation of yi by n would be y bar, where y bar is the mean of all yi's, and summation of xi by n would be x bar, where xi is the mean of all xi's. Moving on, we find the gradient of j of m0, m with respect to m and equate it to 0. Let's recollect the original j of m0, m equation that we wrote. This might be slightly complex mathematics, but let us solve it together. The derivative can be expanded as minus 2 by n summation of xi yi minus m0 xi minus mxi square is equal to 0. We replace the value of m0 with y bar minus mx bar, which was found by us earlier. This is how we expand it. Finally, our goal is to obtain the optimal value of m here. So we simplify all the terms and we group the terms that contain m on the LHS and bring all the other terms to the RHS. Finally, we have the value of m to be y bar summation xi minus summation xi yi divided by x bar summation xi minus summation of xi square. Writing down both the equations for m and m0, we can finally substitute these values into the line equation format to find the correct fit line to our data. As discussed earlier, we will now work on an alternative approach that can be used when the inverse of x transpose x does not exist. What does it mean to say an inverse of x transpose x does not exist? It means that the columns of x transpose x are not independent and that the determinant of x transpose x is equal to 0. So what is the solution for such a case? We will use something called as the gradient descent. And the approach of gradient descent does not require us to have an inverse. Gradient descent is an iterative approach of updating the values of m and m0 such that we move closer to the optimal value of m and m0. The gradient descent update equation is m at t plus 1 equals m at t minus eta times the gradient with respect to m. Please note that eta here is the learning rate. As we have already evaluated the gradient of j with respect to m earlier, I am directly putting it down as minus 2 by n times x transpose y minus x transpose xm. This can also be simplified to minus 2 by n times x transpose times y minus xm. So the gradient update would be mt plus 1 equals mt plus eta times 2 by n x transpose times y minus x mt. So this approach works even if x transpose x is singular. Now let us look into the single feature case. If you recollect, we obtained m to be y bar times summation xi minus summation of xi yi divided by x bar summation xi minus summation xi square. Now we rewrite this in a slightly different format where we interchange the signs of the numerator and denominator both. We obtain the denominator to be summation of xi square minus 1 by n times summation of xi whole square. The denominator can be rewritten as summation of xi minus x bar whole square. Let us prove this quickly. We will first expand the summation of xi minus x bar whole square as shown. Here we have to keep in mind that x bar is a constant value. So the summation of x bar square actually becomes n times x bar square. Then we substitute the value of x bar as 1 by n times summation of xi. We can also simplify 2x bar times summation of xi as shown. Finally, we obtain the relation that we showed earlier. Now, in this case, when denominator equals summation of xi minus x bar whole square, m is not defined when the denominator is equal to 0, which means when xi minus x bar whole square is equal to 0 for all I, the value of m is not defined. This means that for all I, the values of xi are directly equal to the mean, which is x bar, which means there exists only one feature or the values of all features are equal. From earlier, we know that j of m0, m is 1 by n times summation of yi minus yi cap whole square. We again replace the value of yi cap and then obtain the gradient of j of m0, m with respect to m0. This can be written as minus 2 by n times summation of yi minus yi cap. The update equation with respect to m0 is m0 at t plus 1 equals m0 at t plus eta times 2 by n into summation yi minus yi cap. We find the gradient with respect to m and write the update equation as m at t plus 1 equals m at t plus eta times 2 by n into summation of yi minus yi cap into xi. Finally, we iterate through both of these equations until convergence and use the final m0 and m values that we obtained for the line equation. This gives our linear regression solution. Hope you guys enjoyed that. Next video would be upon the probabilistic part of linear regression. Until then, don't forget to subscribe and hit the bell icon. Thank you.